All right, here we are in chapter 9 where we're going to be talking about conic sections. And conic sections are shapes that are created by taking two cones stacked nose to nose, so to speak, and then passing a plane through them. And a plane is a flat surface. And the first of the conic sections that we're going to talk about are the ellipse, and the ellipse comes with a specific definition, which you are welcome to read. But the key aspects of the ellipse are maybe these 2 points, which are always inside the ellipse. Those are called the foci. Singular would be focus, plural is foci. And your author, or the author of this material, calls these the vertices. I like to call each of them a major vertex because they are at the end of the major axis, and the major axis is the longer axis. The minor axis is the shorter one, in which case I would call this and this a minor vertex. I also tend to call this a major radius, in which case the shorter one would be a minor radius. That's just half the length of the major axis. So those are some perhaps non-traditional terms that I'm going to use, and I want to make sure that we're all on the same page. All right, we don't need that anymore. Let's go down here and check out the standard form of an ellipse. So the equation for an ellipse is going to look like one of these two equations, and the primary difference between these two equations is which of the denominators is either larger or smaller. And the process for the calculation of the distance from the center, if you look in the middle of the page here, from the center of an ellipse, the distance from there out to one of the foci is c, whether it's in the vertical direction or if it's in the horizontal direction. And the calculation of c comes from this little equation here, c squared equals a squared minus b squared. Where do the a squared and b squared come from? They come from the denominators of the fractions that are part of the equation for the ellipse. How do I know which one's which? Well, c squared is definitely going to be a positive number. In order to do this subtraction of a squared minus b squared and get a positive number, a squared better be larger than b squared. So I don't actually spend all that much time focusing on whether a is greater than b is greater than a squared is bigger than b squared. I'm not going to focus on it here when we're talking about an ellipse, and I'm not going to focus on it in subsequent sections. What I'm going to try to do is focus on trying to show you a way to have it make sense so that you don't have to be memorizing things like this. Although, if you're good at memorizing stuff, you're welcome to do that. I, however, stink at memorizing, so I'm not going to do that. So we've got the focus. We talked about that, and I've now drawn all over this page. Let's see how quickly I can erase this stuff. All right, so we've got the focus, and there's another focus down below that at 0, negative c. Over here there's a focus at c0 and negative c0 to the left of that point. So we have the foci, we have the center, and the center is going to move around in a moment on a following page. And we've got the vertices, both a major vertex, right, because this point right here is at the end of the major axis, which is the long axis. At least it looks like it's the long axis. And we have a minor vertex. And look at the distance from the center to the major vertex. It's a distance of a. We can see the a right there. Where did that a come from? Well, it came from the denominator of one of the equations up here. Well, as pertains to this graph on the right, does this graph match up with this equation or the one to the left of it? The graph that I've circled does pertain to this equation that's on the right. And how do I know that? Because this vertical distance A that goes from the center up to the vertex, that distance, this distance right here, is in the vertical direction. That distance A is in the vertical direction. And look at this value A up here in this little box. That denominator of A is under the y variable. So I'm not surprised that the distance of A is going from the center and in the y direction. Similarly, the distance here on the graph from the center over to the vertex that's in the x direction, that distance of B, we can find that B value underneath the x variable. All right, we're going to see a whole bunch of that. Let's go to the bottom half of this page and graph one of these for ourselves. So far, this equation right here does not look exactly like either of the two equations at the top of this page. We're going to have to take this equation and divide the entire thing by 36 so that the right-hand side of the equation becomes a 1. So let's do that.
We'll divide this by 36, then this term by 36. We're distributing our division right away. 9 over 36 reduces to a 1 over 4, so we've got x squared over 4. Plus 4 over 36 reduces to 1 over 9. The 36 divided by 36, anything divided by itself is 1.
Great. We now have the equation for our ellipse. The center of this ellipse is at 0, 0. Very soon we're going to change the location of the center, but for this equation, the center is at 0, 0. My radii in the x direction are going to be 2 units left and right of the origin, or of the center of the ellipse, because the square root of 4 is equal to 2, and it's in the x direction. In the y direction, from the center, we're going to go 3 units above and below in order to get to those vertices. Okay, so let's start here at the origin, which is the center. We'll go up 3 units and down 3 units from the center. We'll then go 2 units to the right of the center and to the left of the center, and we can do our best to draw an ellipse. Freehanding on a tablet. Not my best ellipse, not my worst. Okay, so that's what the graph is going to look like. And we also want to locate the foci. To find the distance from the center to either one of the foci, we're going to use the equation c squared equals a squared minus b squared. In this case, c squared is equal to, now remember, it's got to be the larger of the denominators minus the smaller in order to get a positive number. And so that I don't go off the page, I'm going to slide over here and say that c is equal to the square root of 5, or you could say plus or minus the square root of 5. Now the square root of 5 is a little bit more than 2, so I'm just going to ballpark the location on the graph of my foci. Now how did I know to draw my foci in those two locations, above and below the center? Because the foci will always be located on the major axis. And if we glance just for a moment back up into the middle of the blue box in the top half of the page, we see that the foci are on the major axis, c units from the center. And there's that equation that we used in order to find the distance from the center to the foci. All right, that's a good introduction to the ellipse. If we wanted, just real quick, where should we write this? Maybe to the left of our graph. I'm going to write down the coordinates of my foci. Coordinates x comma y are going to be 0 units in the x direction, and then plus or minus square root of 5 units in the y direction. Depending on how you're entering these answers, you might have to enter these coordinates as separate coordinates separated by a comma. So 0 comma the square root of 5, comma 0 comma negative square root of 5. Just be aware that you might have to enter them as 2 separate coordinates, or ordered pairs rather, separated by a comma. Let's move down to page 3. In this example, we're being given foci and vertices. Let's do one of these. I'm not going to do the you try it example, or this video gets long and file sizes get large, but I think this one will get you started. These two problems are very similar to each other, and if the foci are at -2 and +2, already I'm like, I can't see this. Well, it's because I haven't drawn it. I haven't seen any of this stuff on a graph. So just at the top of my paper here, I'm going to, if you printed out these printable notes, if you have access to those, you could just draw yourself a little sketch at the top of the page. My foci are 2 units to the left and to the right of the origin. My vertices are 6 units to the left, 2, 3, 4, 5, 6 units. 2, 3, 4, 5, 6 units to the right. Okay, so is my ellipse going to be wider than it is tall or taller than it is wide? Well, I know that my foci are going to be on the major axis, which is the long axis, so my ellipse is going to be wider than it is tall. What about the distance from the center of this ellipse, which is at the origin still, up to either of my minor vertices? What's this distance going to be? Well, from the center to a focus is C. In the x direction, right, and I don't even know if I'm supposed to label this as A or B. Oh wait, I do. This must be A because it's the larger of the two distances, because this is my major radius, as I like to call it. So that's going to be my A value, the larger of the two denominators, which end up getting squared. And I also know that C squared is equal to A squared minus B squared, which means that 2 squared in this problem is equal to 6 squared minus B squared. And if we solve for B, let's solve for B squared just for starters. I've got 36 minus 4, which is 32. That's equal to B squared. And I could take the square root of both sides in order to find my B value. But do I really need my B value? As it turns out, I don't, because the standard form for the equation of an ellipse is x squared over a squared plus y squared over b squared equals 1. I can find out my a squared value by taking my horizontal radius and squaring it. So we already know that that was 6. It's going to turn into a 36. So I have x squared over 36 plus y squared over my b value, which we determined is actually the square root of 32, but I don't need my b value. What I need is b squared, and I already know what that is. It's 32, so I can write in my 32 there, set it equal to 1, and we have in standard form the equation of our ellipse. Let's just make sure that we're writing that in the right form. Standard form for the equation of an ellipse. There they are, looking good. What we're seeing on the bottom half of this page is that you can take an ellipse and move it around the coordinate plane. So the center of the ellipse is not always going to be at 0, 0. The coordinates of the center, and this happens for parabolas, and we're going to see it for some of the other conic sections, or I guess all the rest of the conic sections. When we translate a graph or shift it horizontally, vertically, stretch it, reflect it, you've seen these kinds of operations performed on parabolas and square root graphs. Very often, the center or a vertex is located at h comma k. And we're seeing h and k inside the parentheses here. And what we have to do is be careful, because this minus sign that's in front of the h or in front of the k can tend to mess us up and cause us to get incorrect coordinates for our center. For example, in this problem, example number 3, let's find the center immediately, the center of our ellipse. The center is located, we were just saying, at h comma k. And in this case, what's my h value? Well, as we saw on the previous page, this numerator should say x minus h quantity squared. I see the x value, I see the minus sign. Looks like my h value is a positive 1, just from matching up the pieces. But what a lot of people are tempted to do is to see this negative 1 right here. That didn't go very well. Nor did that. There we go. Is to see this negative 1 right here and say that h is equal to negative 1, when in fact it's not. It's equal to positive 1, as we saw by matching up the pieces. One way that you can think of it is that that negative 1 ends up being the opposite of the actual x-coordinate. Whatever ends up working for you. Following that kind of pattern recognition, I would look at this positive 2 right here that's next to my y value, and I would say that the y-coordinate of my center is the opposite of that, which would be negative 2. And then as long as we're at it, let's go ahead and plot that point. Positive 1 in the x direction, down 2 in the y direction, there's my center. Okay, what about the length of the horizontal radius? The horizontal radius is the square root of 16. I know that it's the horizontal radius. I know that it's horizontal because the 16 is located underneath my x variable. So that's going to be equal to 4, or plus or minus 4. The vertical radius will be the square root of the denominator that's under my y value, which is the square root of 9, so 3, or plus or minus 3. Let's go over to the graph and plot some more points. From my center, I'm going to go 4 units to the right. 1, 2, 3, 4, and plot a point. 1, 2, 3, 4 units to the left, plot a point. Vertical radius is 3, so again, starting at the center, let's go up 1, 2, 3. From the center, down 1, 2, 3. There we go. This thing's going to look almost like a circle. Maybe we can exaggerate it a little bit, almost flattening it out a bit along the top to make it look like it's indeed wider than it is tall, because we know that it is, horizontal radius being 4, vertical only being 3. All right, so that's a pretty accurate graph, except for the part where it's hand-drawn. And then, just briefly, let's find the distance from the center to the focus. To do that, we're going to need our trusty c squared equals a squared minus b squared equation. We don't know what our c value is yet, but I know a squared, in fact, is 16. It's that denominator under my x value. It's my larger denominator is already a squared, so we can just put the 16 right in there. Minus b squared is 9 from our smaller denominator. Good. That's equal to 7. And our c value is the square root of 7. Oh, the square root of 7. That's a terrible number. Well, the square root of 4 would be 2, and the square root of 9 would be 3. So it's somewhere between 2 and 3. What's 2.5 squared? 6.25, so it's got to be bigger than that. So a little bigger than 2.5. And remember that it's got to go, I'm just going to say approximately equals with a squiggly equal sign, 2.6. Right? I'm not using a calculator. I'm just ballparking it. From the center, we're going to go approximately 2.6 units to the left and right of the center, because the horizontal axis is our major axis. It's the longer one. And we know that our foci are always on our major axis. So I'm starting at the center. I'm going 1, 2, and more than 2.5 units to get to this focus. I'll go back to the center, to the left 1, 2, more than 2.5 units to get to that focus. And if you want to switch colors of your pen, or if you want to go and label these, those are your foci, F-O-C-I. And the foci, remember that we got to those two locations by starting at our center, which had an x-coordinate of positive 1, and then we moved in the positive or the negative direction. I'm not going to say 2.6, I'm going to use the exact value of the square root of 7. So we started at 1, and we went left and right the square root of 7 horizontally to get to our foci, but vertically we didn't change at all, so our foci still have y coordinates of -2, just like the center. Did we graph the ellipse? Yes. Did we locate the foci? Yes. Not only did we locate them on our graph, but we found their exact locations. We're good. Again, my recommendation on this one is draw a picture, find and label everything that you can, and then fill in the blanks. You've got the endpoints for your major axis, you've got the endpoints for your minor axis, so you can find the center by going to the midpoint. I really hate writing with a digital pen, although I was being pretty lazy right there, let's be honest. The center will be located at the midpoint of either one of those axes, both of them in fact, and then once you've got that picture, you can figure out your A value and your B value, and from there you can find your C value, which is the distance from the center to the foci. And lastly, is it lastly? Well, pretty close for this section. In example 5, we're going to complete the square in order to write this equation in standard form, so just a quick reminder of this process. First, we're going to do some organizational stuff. We'll take our x terms and write them first, so we have 4x squared minus 32x, and then our y terms plus 9, y squared plus 36y, and then I'm going to subtract the 64 over to the right hand side. I don't want that thing on my left hand side. We'll put some other constant values over there. Then I'm going to do something so I just wrote a little note that I reordered stuff on the left hand side, and if you want to, you could also put in a minus 64 that you subtracted 64 from both sides. Then I'm actually going to come into these first two terms and I'm going to factor, and I'm going to do some factoring in here, but not as much as you might think. I'm only going to factor a 4 out, so that on the inside, or in my leftovers as I like to say, I'm going to have an x squared minus 8x, and then I'm going to leave space to have a little additional something in here after my 8x. And then similar strategy in my other two terms, they share a common factor of 9. I'm going to pull that out, not pulling out a 9y, just pulling out a 9, so that I've got y squared plus 9y plus something else. And then on the right hand side of the equation, the negative 64 is still there, but remember, what you do to one side of an equation, you have to do to the other. What did we do to the left hand side? Well, we added one of those, didn't we? No, we did not. We added 4 of those. And we added one of those, didn't we? No, we did not. We added 9 of those. So that has to be reflected on the right hand side. Let's put that in. Let's stay with orange. So I'm going to add, because there's a positive 4 on the left hand side, and it's 4 of those, and then a positive 9. So we've got 9 of those. All right, so this is the single or the regular looking arrow. These are these goofy squiggly looking arrows that I drew. Now what goes into those positions? What goes in here and what goes in here? I'm going to determine that by taking this negative 8. I'm going to divide it by 2. I'll take the result and I'll square it. Negative 8 divided by 2 is negative 4. Negative 4 squared is positive 16. Always going to be positive. I'm squaring it, which means that this is always going to be positive. So that's how I need to put a plus sign right here. And that 16 is going to go into that position. And then I'm also going to come over and take this 9. Wait, 9 times 9 is 81. That's not right. This doesn't say 81. Boy, this is supposed to be a 4 right here. All right, if you'll do me a favor, go into your notes and make sure that this 9 becomes a 4. This 9 was okay, which means that this 9 is okay, so we don't have to worry about that. But make sure that this one turns into a 4. Thank you. So we're going to take this 4, divide it by 2, square it, and we're going to get a 4. Taking a 9 and dividing it by 2 right here, I thought, that's not right. I don't remember getting a decimal. That was my clue that I had made a mistake. All right, so the 16 and the 4 are going to go into those two positions, which means we're going to take a 16, we're going to put it over here. We're also going to take a 4, put it over there. Let's fill in the blanks. Now we've got 4x squared minus 8x plus 16 plus 9 times the quantity, y squared plus 4y plus 4 equals, and then we're going to have to do some arithmetic over here. We've got negative 64 plus 4 times 16 plus 9 times 4. That looks to me like a total of 25 4s, and I'm pretty sure that this is 16 4s, 16, 32, 64. Oh, but we're taking away 16 4s, and this is 25 4s. What's 25 minus 16? 9, so we're left with 9 4s, 9, 18. I think the right-hand side of our equation is going to become 36. And on the left-hand side of our equation, this is factorable, and so is this. They're perfect squares. We designed them that way. So the left-hand side, when we factor, becomes 4 times the quantity x minus 4 squared plus 9 times the quantity y plus 2 squared. And the right-hand side does indeed turn out to be 36, just doing a little quick math over there. In order to be in standard form, the right-hand side of our equation must say 1. So we're going to divide both sides by 36. And if you want to put divided by 36, divided by 36, divided by 36, you can. If you want to do what I prefer to do because it takes up less space and requires less of my messy handwriting, I just put a little note over here that I'm going to divide both sides by 36, and then I get on with my life and write the result of doing that division. 4 divided by 36 is going to reduce to division by 9, so I've got, I don't even need the parentheses. X, oh yeah I do, it's still squared. X minus 4 squared, that's divided by 9, because 4 divided by 36 reduced to 1 over 9, plus this 9 divided by 36 is going to reduce to 1 over 4, so we have y plus 2 quantity squared over 4 equals, and then 36 divided by 36 reduces to a 1. We've got that 1 on the right-hand side that we needed, and we've got the equation for our ellipse. The location, just for fun, of the center of this ellipse is, I'll give you a second to think about it, it's h comma k. Remember that these values are kind of backwards from what you might think. Look over here, right? We talked about this and we talked about this. It's actually positive 4 for an x coordinate and negative 2 for a y coordinate. I was writing in orange, then I changed to black. Sorry. All right, so those are the coordinates of our center. How wide is this thing? Well, it has a horizontal, give me a different color. We need more colors. It has a horizontal radius of the square root of 9, so 3 units to the left and right of the center. It's got a vertical radius, as I like to call it, of the square root of 4, which is 2. So from the center, we could draw up 2 and down 2. Those would be our a and b values, respectively. A is larger, so that we could do a squared minus b squared. That would give us c squared. Take the square root of both sides, you got your c value. and that's the distance from your center to the foci. Remember that the foci are located on the major or long axis. And then the very last thing in this section of notes, they're asking us to write the equation of each of these graphs. I suppose we could do that. We don't really have enough room, but maybe, can I create more room? I don't know if that's helpful. Let's just do this one. I've got x minus the x-coordinate of -1 squared over my horizontal radius, which is 2 squared. So that's x minus h squared over a squared, because my horizontal radius is my long radius, plus, in the numerator, I've got y minus k, which is y minus a positive 1. That's the y-coordinate of my vertex, or sorry, my center, divided by the vertical radius, which is a 1 squared. Standard form, this has to equal 1, and then we would just clean this up a little bit, and we get x plus 1 squared over 4 plus y minus 1 squared over 1 equals 1. And that's the equation of our middle ellipse there. All right, I hope that's helpful. I know that some of that stuff I kind of rattled through quickly, so go back and listen again and again and again and again, and pause and try to work some of these things out on your own. Go back to the beginning, and before I start working out one of these problems, pause it, try to work the thing out for yourself and identify all of the components on your own, and then push play and see if the answers that you're getting are the answers that I'm getting, remembering full well that I am human and it's possible that I'm going to make a mistake. I try to catch them and put fixes right into the video. Is it possible that I'll miss one? Absolutely. All right, next time I see you'll be in 9.2. Thanks so much. Peace.